All right, let's see. I think we're live now. And it appears that way. All right. Looks like we got a little bit of lag, but it's only about 15 seconds, so that should be fun. But we got good stream health, so we're good. So that's really nice. Okay. Well, here we are for another QA session. I've been getting a lot of good feedback on these, so I'm going to do a few of them. And it's been really great in the Crocs Gitter. There's a contributor, this feller by the name, he's in Australia, but it's a feller by the name of Dale Francis. But he's been putting in like little challenges and things like, hey, how do you solve this problem? Well, by he's been putting him in, I mean he's put 2 in so far. Hopefully he keeps the trend going. But it's kind of neat because you get to see other, people in the Crocs community try new things with different answers. So this is actually the first exercise, or the first thing we're going to look at. And by the way, this whole thing is kind of centered around pair. Pair is one of my favorite data types. There's so much you can do with the pair. And then we're going to talk a little bit, we'll be able to talk just a little bit of how the pair that Croc ships with, boy, that's hard to say, is actually, I kind of like to call it a tagged pair. Because the way it's set up, we everything pretty much focuses to the right. So that allows you to tag some certain value on the left side. Like you have chain and AP and all that. They even go on the right. One of the things I'm thinking about changing, and if anybody has any feedback on this, I have it because it's set up as a tagged pair. When you do traversals on it, it kind of acts like a tagged identity, right? So it does the same traverse that you would do on an identity over the far right side or the second. But I'm not finding when I use a pair for a traversal that I'm not really using it in the tagged context a lot. Like I would rather have a pair of 2 maybes, a maybe on the left and a maybe on the right, and then get back a maybe of pair that has the 2 values in it, like how you would traverse over an array. So I did have it set up to where it only traverses over the far right value, ignoring the left, and just gives you back the left because it's set up to be a tagged pair. So I'm actually thinking about keeping like the chain, the AP, and the map, keep those for doing tagging, but then have the traversal actually be a traversal like you would expect, right? Like, again, if I have a pair of maybe, I would like to traverse that into a pair, whatever the A's were in there. And it's kind of great too, because you could have 2 separate like maybes, like a maybe of A and a maybe of B. Yeah, see, that's the thing with the pair. I don't know. I need to think about this a little more. But anyway, because it's real easy like to do a traverse on a list because you typically have a list all of the same type. But the whole thing of a pair, I don't know. I'll have to think about that traversal. But right now, the traverse is set up so it will act like a tagging pair. So we're going to see a couple examples of like how and why this is a tagged pair. So the first one we're going to look at, this comes from, like I was saying, on the Gitter. Let's see here. Let's go to Gitter Crocs. On the Gitter, there's this feller. There we go. This guy, Dale Francis, he's been putting in all of these little, brain teasers, like how would you implement this? And everybody just goes in, and it's been a fun time. He's done 2 of them so far. I hope he keeps it up. But you get a lot of people putting up solutions and things like that. So if you want to send brain teasers, just head over to the Gitter and then you could set those up there. But this comes from this challenge. He was doing a refactor at work. And I pretty much took the code out of here and I'm going to present a couple of the examples because they're kind of neat. So this is... Oh, goodness gracious, I can't find it. But I have the imperative code that he was refactoring here. So basically, What this does, and I'm a little skeptical about this, especially this visa here, like what happens if it's not within the proper range, like a 49999 or something like that. Anyway, there's some questions I have about this, but this was what was presented. So we're just gonna kind of go over it and come up with a couple solutions. So when I tend to approach these types of things, I'll go in and be like, hold on, let me get a sip of something here. I'll start looking for patterns on things, right? So an immediate pattern here, this is basically just a switch case. And it's basically if one of these are true, the first time that this is true, it's going to return some sort of thing saying that this is this type of card, right? We could also have, basically that's it. So here, how we're determining that is we're building out a new regex each time. Like this is very imperative. And then we're using that to match to see if it's, actually has a match. A couple things about this, like this could be, instead of a new regex, you could just put the regex there, things like that. This should probably be a test because you could do the test over it because this is all preface to or prefix to the beginning, right? So any number starting with is what I'm looking for. So like this could be a test instead of a match, whether it's true or false, and then if everything's good, return. But basically, this is just taking data, and we can look at this here. Let's jump over here. So we put in some sort of card number, and it kicks back, like if we look over here, diners. Gives you two split things like that. So to go over how I would have approached this, or one way, and it's part of the solution that I went in there, part of the solution that I submitted for the get, is I kind of see this as, well, first of all, since we have an early exit, it seems like order matters. And we see that order does matter because if we match on a 3-0 to this, to that, this could, if this was in a different way, it could falsely report other cards. So order matters on how we exit out of here. So for me, I'm thinking first, right? I'm thinking using the first monoid some way, somehow. The other thing we're doing is it's basically just a check on this regular expression, right? So what this really is just a predicate function against some sort of value, right? So since order matters, we would like to maybe come up with some sort of structure that instead of doing a regex match, we actually run a value against a predicate function. And if that predicate function returns, then we just go ahead and return whatever that tag is or the value that it's been classified as. This is basically just a classifier of some kind. And we can make it be a classifier over a predicate. So already my mind's racing and I'm like, oh, goodness gracious. Really, the only thing that matters here is this predicate and this. So automatically I could think I have two things, right? And two things that vary. So not even thinking of parallelization, if I start thinking about this is a tagged pair, I basically have a tag and a predicate that signifies what that, like if that tag is valid. It gives me a way to tag some sort of value in one way or another. That's basically what this thing is doing. So what I want to do, if I want to tag a value, I probably want to tag the predicate that goes with that value. So now I'm thinking, instead of having this, what if we were to take any data structure that was a pair of some sort and has a tag and a predicate function associated with that? So it would look something like this, right? So let's do a const data. Now's the time when we code. It does a const data. And one of the things, I'm going to get a little sidetracked here just for a moment. You know what? I wonder what happens if I move my camera. It's weird talking over here to you. Anyway, so one of the nice things slash bad things about the array data type is you can use it as a list, and most of the time that you're using it as a list, with an empty value and then a what is that, indeterministic amount of values there. Like if you're using it as a list, typically they're the same type. But because the type can vary, and it's not like a list in say Haskell or things like that, you can actually just use it as a product type. So it's basically a poor person's product type if we want to use it that way. So instead of using the pair or anything like that, we can get some value out of just using an array as a pair. And that's because of like destructuring on functions, basically destructuring, right? We don't need to like call FST or SND on this. We can just destructure the first two elements off, and now we have our left and our right, or our first and our second, or our FST and our SND, right? So we can put our tag here, and let's make a tag of small, okay? And now let's have a predicate that goes with that. So let's see here. We will bring in const greater than or equal to, and we will grab this from Ramda. Okay. So here we'll just do greater than or equal to. And let's grab a less than or equal to from Ramda. And by the way, if you guys got any questions or anything as we get into this, because at this point I'm going to kind of just sail through it, feel free to just stop in the chat or just say, hey, I got a question, things like that. I'm more than happy to stop and answer them just to make sure that we're all, on the same page here. So for small, we want to do something like greater than or equal to, let's see here. And actually for small, we want to do less than or equal to 50. Okay. And let's see, we'll make a medium. And let's say this is, let's bring in and here. So we'll do const, is it and or is it or? Yep, it's and. So we'll bring and in from crocs. All right. So for this, we just want to do an and. Is it greater than? I always forget my Ramda. So yeah, pro tip, you always want to look, everybody looks up documentation. Okay, so here we want to do greater than 50. And I'm using this and because the and here actually takes, it doesn't take functions, it actually does values. Whereas the and in crocs logic actually takes the functions themselves. So that's why I'm using this and, just it makes it easier to have the and, take the functions. So the first thing we want to check to see if it's greater than or equal to that, and less than or equal to 100. And this will be greater than 100. And perfect. Okay. So now basically this is going to check to see if something is small, it's going to be less than or equal to 50. If something is, medium, blah, blah, blah. So we have a nice little range picker here. And then each one of these are tagged with a value that represents, it's basically the tag in a pair. Yep. So what we need now is a function that will actually go through and run through these and pull out the proper tag that we want for this, right? So let's create a little thing called tag value. And what tag value will do, how many people? Oh, we got 6 people. Welcome. A real bummer about this platform is it doesn't tell you who's entered. So I used to be able to say, hey, welcome, this, that, or the other. on like say live code edu or other things. So I'm not being rude, I just don't know if you come in. So if you want a little greeting or something like that, just say hey, and then I can respond back to you. It's one thing that I miss from the other bits is it doesn't provide any identity. And I guess maybe that's because anonymous people can watch or things like that. But, oh, and we lost one. See, I shouldn't explain such things. All right, so what we want to do is we need a function, and let's see here. The aim here, what we're trying to do is take this data, and let's actually call this preds. Okay, so these are our predicates and our tagged predicates. So what we want to do is take a value and then run it over each one of these. And if everything is all good, then we want to return whatever the tag is. So if for the first one that passes, we basically want to do that. Pretty easy, pretty normal stuff. So one of the things we could do before we kind of get into this is think about how it would do it for each one, right? So since we have a predicate, we can bring in a helper called safe. And what safe does is it captures disjunction. I give it some sort of predicate, and if that predicate passes with a value that it receives, then it's going to wrap it in a just. If it does not pass the predicate, then it gives back a nothing. So basically what we want to do on each one of these, in order for like to test each one, we want to be able to lift this into a safe, and if that passes the check, we're going to need something else called option. And what option does is it takes a maybe, and if it's false, it takes a value, and if that maybe, and then a maybe, and if the maybe is a nothing, then it returns that value. If that maybe is something or a just, it'll actually give you back the just value. So it's a way of unwrapping your disjunction, like once you're at the end, you know? Observing it, I guess, at that point. We observe it in our JavaScript world by saying option it out. And then at that point, we either observe the value or we observe what the nothing is. And it allows us anyway, that's stupid to go on and on about this stuff. So we're going to need two things here. First, it would be really nice to have our XS's or our preds come in first. Okay. And let's call this tests or tagged preds. And actually, we don't want this yet because we need to get the first case for it. So the first case for it, like to get a value, is we're going to need the actual predicate, the thing that we're running against. So we'll call this tag. And then here we'll grab the pred off of it. So now when we get one of these, it's going to put this as the tag and this is the pred. And then from there we want to, take the value, right? Whatever the value is that we want to run against it to actually get the tag. And now we just do a simple composition. And how do we want to do this? So we basically want to take the safe that we have. We brought in that safe function, and then okay, so we have safe and then pred. This will grab the actual pred off of it. And then from there, we want to option that to be the value. To be our default. What do we want that to be? So if it's good, we don't want to option this yet. We actually want to map over, that's right, and do a constant of tag. All right, so now we need to bring in some of this stuff. We don't need option yet, but we do need compose. So we'll bring compose in, and we need constant. So we'll bring constant in. And then we need map, so we'll bring map in. And that is not constant. All right, so there we go. Now we have that. The thing we want to do now, though, is then lift this value. So we can do that, or not lift this value, but apply this value, I should say. We could do that, or we could do this with curry. And take the value in like so. And then we just bring curry in. So one of the differences, again, between the curry and Crocs versus the curry and Ramda is you could do this without specifying it, and it will do your partial application stuff the way that you expect. So that's a fun thing. So this will actually give us back, if we call this tag value. This is going to take, let's call them preds, which will be what this is. All right, so we take a list of pred, and this is a list of pred. And don't be confused with the predicate. Oh, I just thought of another idea. I'll save that for another time. Okay, so we'll bring in our list of preds, and then we take our value. And actually, let's not call it that. Let's call it a, when I do this, I mean an array that's acting as a product type, right? So here we're going to take some sort of B, and then we're going to have an A to B, or A to Boolean, right? And then we take a value of A. Oh, come on. We take a value of A, and then we give back a B. So it basically has the, and we don't have a list of preds. Sorry, I'm getting way ahead of myself. We don't have a list of preds yet. We actually have a pair that has a value B in it, and then we have a predicate that takes an A to a Boolean. And then from there, we have this, which returns a maybe of B. So now that's going to be a maybe of B. So we either, and B, of course, is, we'll call this, we'll do B. And then we have an A to a Boolean. Okay. So that's a list of these things. We can call them whatever we want, tagged, pred, something like that. But that's what this is. Just so we can follow with the types. Because it's going to get kind of weird. We're going to have to do some flipping and things like that. Okay, so now that we have that, let's see. We now have this tag value. Let's see if this actually works. I don't think it's going to, but let's see. So let's do tag value, and we're going to tag value with 4. And we need to bring in our tagged preds. Oops. Pred. That should be an S, because it's a list. And then we can actually do this, make this a tagged pred, and then say that this is a tagged pred, just to clean this up a little bit. And this is a list of tagged preds. There we go. Okay, and then this gives back a maybe of B. So here we can say this takes a tagged pred. And I guess we'll do... Yeah, we need to represent that a little better. Let's just call tagged pred. We know what A is, B is. There's a better way to do that. All right, so now let's do tagged preds. And pred or predicate function is required for that. Why? Oh, because I need to actually specify. So what we can do is come in here and grab the first one. So that, of course, is going to be a nothing. Why is that a nothing? Less than or equal to... Oh, do I need to flip these? Are you kidding me right now? Oh, man, I tried to be... All right, so greater than takes an A to an A. 2 is greater than or equal to 1. True. If the first argument is greater, that's weird. All right, so I have to flip all of these. So what we'll do is use rflip because it lets you partially apply. Gosh darn it to heck. I should have tried that out. All right, so here we'll just do flip and copy this over. Sorry about this. Okay, and do the same thing here, flip. That's really weird that that's not very point-free-ish, right? That doesn't seem very point-free-ish to me. Maybe I don't understand it, but... Okay, and here we'll just do another flip on greater than. You know what? I should have just flipped all of these at once, but whatever. Hey, you live, you learn. All right, so now that it's been flipped, and does that make sense? Because we're going to use this a couple times. So flip will automatically flip and let you apply anything you want to it. I put that in kind of as a feature because most of the time you're flipping and applying so you can do something. So it just works with the curry. So I never really thought we don't need this imperative anymore. We'll get that later. So anyway, that's how the flip works there. So here we have our tagged pred. We're able to get that. So now if this is 100, that's interesting. Oh, because that we didn't pick it. That's ridiculous. All right. So that's nothing, but then if I pick the proper one, that comes back as medium. So what we could do now is actually fold on this, right? And if we think about it, we have a really, really neat tool at our disposal that will allow us to fold over a monoid, right? Now we have this cool monoid here, and since we already have a maybe, see how it's in a maybe? This is going to work very well with this. So we could take our first monoid, and what the first monoid does is it actually provides the first value from the first. Every time that you concat to it, it's going to provide, it will never overwrite that value. So when order matters, so for instance, say we were to come here and remove this and maybe we just want to make this greater than 100 or greater than 50. Right? Okay, we don't need and. So that's good. It passes that. But what if we make this 150? It also passes that. So order does matter, right? So if we would want this to actually check because we're using greater than, and really we should be using less than or equal to, but it's bad for this example. But anyway, whole other story around that. Just for now, we'll just do it this way. But see how order does matter? Because we're going to pass on large here as well, and we would pass on medium. So what we really want to do when we're reducing this down, see how we pass on medium, is get the first one. And to do that, we can do that with this first one. And if you look here, so since it doesn't pass this one, I get a nothing back. If we look at the empty here, we see that the empty that it gives back is a nothing. So nothing can be treated as an empty, which means it doesn't concat, it doesn't do anything like that. Oh, hold on. So it doesn't concat, it doesn't do anything like that, right? Empty is a constructor method. Bam. All right. So since we have a way to say, hey, this is empty, we can now really fold this down pretty simply. And to get this to apply, we can now come up with a little thing that we'll call, goodness gracious, what's a good name for it? Still got 4 people. Woohoo! We'll call it match. And then match is basically just going to take what I like to call, what did we call them? Tagged preds. And then from there, it's going to take back it's going to take an A of some kind. And here it's going to give back a B. And we know what B is from here, but like I said, there's probably a better way of doing this. Anyway, a better way of writing those types out. So I guess before we go on to the next thing, does all of this make sense? Like what we're doing? I'll take silence after about 30 seconds as nothing. Is there any questions or anything about any of this? Does it make sense how we're setting this up? Okay. All right. So now that we have this match here, or now that we have this, let's get ready to rumble. We have this thing called mconcat, mconcat. Let's use actually mreduce map. And what mreduce map does, let's go down to functions just so we can see. This is a helper, and let's jump down to, it's better to just do this. So we'll go functions, and we'll go mconcat. Oh, mreduce. So what mreduce map does is it takes a foldable. Well, the first thing it takes is a monoid. And really it takes a monoid type rep. I should fix this. But it actually takes a type representative for the monoid, or the constructor basically. And then it takes something that goes from a B to an A. And then from there, it will fold on the monoid, basically. It'll give you the monoid. It takes a B to an A, and then we'll get a monoid of an M to an A, and then it'll fold it down, and then return the carrier type. So in a monoid, you have all monoids, you'll notice, have some sort of carrier type associated to them, right? Like for addition, for sum, it's positive numbers or positive. It could be numbers, but integers are preferred, and because then it could be pretty much anything in JavaScript. You can even make it strings if there wasn't type checking or anything. But anyway, so for instance, that's the carrier type for that. Carrier type for what we're doing for this first is actually a maybe of A. So what reduce is going to do, map reduce specifically, let's jump back to here and to here. So what this is going to do for us basically is allow us to take a value and then lift it into the maybe. And then with that maybe, we can go ahead and fold on the first. So it's going to pass that maybe back to us, right? So let's bring in first, and that's going to be the actual monoid that we're going to use to do our concatenation. So we'll bring in first, and we need to bring in mConcatMap, or mReduce. Okay, so now we need a function because we need to take the mapping function. Because right now, all we have is the tagged value and the other thing, right? So here, we need to go ahead and provide, the first thing that we need to provide is we need to have a value to map to it, right? But the thing with this is we need to, how would you say, map over these. Like we need to reduce on this. So we have a problem here, Mr. Lawrence. So we're going to need to have to bring in our x, or what our value is, like this. And then we want to go ahead and take in the whole list of things, right? So here we want to then do, since this, oh, and see, this is silly because this actually takes this as well, or this takes the tagged pred first. So is that what we want? So let's see here. We have an x. We don't have the tagged preds. We don't have those. So we need to partially apply our x to this first. So we want to do tagged value and then apply our x. But if we look, because that's all we have that x and that's it. So if we look though, this does not match that signature. But that's okay because we can just do flip instead of curry. And it doesn't really matter. It's going to flip this function and do everything like that. So now we can do some of this and then, oops, then a whole bunch of that. And now we have a tag value, even though it's a little strange. We could just do the flip here because that might make more sense. So what we could do here is do the flip here. And that might be a little better because it keeps things copacetic, right? So now we're going to flip and then apply that to it. And now we're ready to take, let's see here. Well, we have the x first, so we're going to have to do another flip here. But don't worry, it knows how to figure it out. It's got it all. So this is going to actually give us back what we want because mReduceMap takes these tagged preds. That's the next argument that it's going to take, is it needs something to reduce on. And then we'll get this x. So now, since we have this flipped, we can actually take the argument that gets applied to mReduceMap and then go ahead and take our x next. And this is better for data first, right? Or how would you say, context first, data last? Because really, we want to set this up and make, a specific function that all it does is we don't want to specify these tagged prads every time, right? So we want to do something like this, where we're all function is equal to match. And actually, let's do that. So we'll do const function. And let's call this match number, I guess. I don't know, for lack of a better thing. And then we want to call match and then apply tagged preds to it. So now we have a function that will work over the tagged preds. And now it's only going to take that, right? So this is how you would use partial application to extend your function life. Now we only need to provide one thing. So we have 150 that gets large, right? It got the large, gives us our just. And if we do 0, it gives us small. And if we do, let's see here. If we do -1, that'll get us small. And that's because we don't really have a boundary. So let's see what happens whenever we set up a boundary here. So we'll bring in and again. And again, we'll use the one from Crocs because it lets you do it with functions. And we will bring this in as that argument. And then let's bring and in. Okay. And here we have our flip, and we want to see if anything is less than 0. So what do we have? We have less than or equal to 0. So we could actually bring in Crocs not. And this also is takes a function. All of the functions take functions. All the predicate function stuff, like and, not, all the predicate logic stuff, all do functions. So here we could just do not, and we will do flip. We got to do this flip thing. I should just done this in one place. This is ridiculous. And we'll do less than or equal to 0. And we get a nothing back. But if we make it 0, then we're good. We should get a small. And we don't. All right, so if not less than or equal to 0, oops. That's not what we want. Logic, man. We'll just do this. Okay, so now we get the small because we got the 0 in there, but if we do -1, then we get our nothing. So now we have a boundary here, right? And now we have a nothing that we can do something with, right? So say we want to, we're putting everything to an actual string. So what we could do with this match is come over here, and we could option it. We'll just do this fluent style to number not valid. So now anytime we get that at our edge, we can actually specify, oh, this isn't valid, things like that. So it seems like really ridiculous, right? Like all of this. And we have this whole complex thing with numbers. Or not with numbers, but with, how would you say, regular expressions on card numbers. Well, the beauty of this is this will work for any structure, any tag. Right now we're using strings, but these could actually be objects. They could be functions that get tagged if a predicate. So now you get a function back that you can run. They could be strings, numbers. They could be anything that you want them to be because you're doing it in a product type. Right? You don't need to limit yourself to whatever your tag is. You can tag it with any other type. You want to tag it with another ADT of some sort? Go ahead and tag it with that. Because it is a product type and it's a bifunctor. So anyway, these tags don't just need to be strings, but we're just representing them as strings right now. So what would that look like with the cards? So here's what we have the data for the cards in, right? We have the same sort of thing that we had before. And let's actually open this in a new tab. So we'll do cards and we will do data. It's like a ghost. So this is basically for our predicates. All we did was we moved over each one of those tests. And we're using just the Ramda test that will test some sort of, how would you say, string. Takes the regex and then tests a string against it. So this is basically exactly what we want. And then it does the tests. So it's basically in the same structure that we have here, except the tag is the card numbers and the predicate is a test on that. So we've made this real general function that will go ahead and try to match a tag with that. So let's see what that looks like. Let's actually call this, I don't know, data. Actually, let's GC this. And then here we'll do const tagged preds. And we will make that equal to require data. Okay, we get a nothing back because this doesn't match any of that stuff. It's bad news bears, things like that. But let's see if we can find one here. Let's start one with 4026. Oops. We can close this out. No, we'll keep that open for later, I guess. All right, so now we can get rid of this. We don't really care. It's the same thing that we're doing. We'll get rid of this. And there's the imperative function, so we'll use that to test against. Okay, and here we have match numbers, needs to be that. So we'll call this match card. Or let's call this tag card. Nah, let's call it match card. Why not? All right, so here we do match card. And we want to put in a value. So this will get us nothing because it's not a valid thing. We'll put in 40. Oh, goodness gracious. What is it? A good Visa one. 4026. And XXXX. XXXXXXX. So now we see we get back our Visa Electron and Visa. So we can put in any of these numbers and we actually get back. We didn't change anything about this code. The only thing we did was came up with a way to encode it in a way that we can work on it generically, right? And by using the pairs, we're able to actually pull the tag out and do what we want with it, right? So yeah, if we put in something that isn't in here, we'll get a nothing back, right? 9999. So that's not a valid card. We get a nothing back. If we want to do 49999, we'll get back the Visa. This is why I don't know if regex is the best solution to this. But we get the other Visa because it passed that. I don't know if that's a valid prefix for that. Also, for MasterCard, we can do let's do 5600. And that's nothing because it needs to be 55. Okay. So one of the things you'll notice, though, about this function is it's a dead end. Like, we passed this function and we said, give me your type. That means that we're going to have this card number just hanging about, right? Because we're going to need to merge it back into the data at some point. Otherwise, the only thing that we're going to have is what type of card this is. So again, this is where mapping with a pair comes in really, really handy. Or I'm sorry, tagging with a pair or using a pair comes in handy. So we're not going to use, we are going to end up with some sort of tagged pair, but we're going to take advantage of parallelization using a pair to actually build our tag out. So now that we have a way to match this card, let's just make a little something called FN. We don't know what to name it yet, but that's what we'll call it. So let's bring in a little something called fan out. And what fan out does, if you remember from last week, is it lets you, it's basically the universal construction for set, for a pair in set, or for a product type in set. It's the construction that proves the, or that shows the universal product, or the universal property on a product. Whatever. It basically lets you run two functions on a given type, and then we'll give you back a pair with the result of each of those functions on either side of the pair. So that way you can run things in parallel, right? So what we want to do here is, now that we have this, it's going to take this match card. So we want to do this FN. It's going to take that number and it's going to split it into a pair. And then it's going to run that value on that to apply that value to whatever function you pass in. So for the left side, we're going to actually do, on the left side is where we want to keep our tag. So we're going to do match card. Match. And we don't need to partially apply any of that because we already took care of that there. So we're going to do match card there. And then here we're going to do identity because we don't want to touch the original value. We still want that hanging around for us to do things with, right? So here let's bring in fan out and we want to bring in identity. So that's HI. That will go here, identity. All right, so now that we have that, we have our FN. We see now that we get on our left side, we get our just MasterCard, and then on the right side, we now have tagged that value with a maybe of whatever that type is. If it's not the right type, that's okay. 9999. We still have that original value, but we have nothing on the left side. So it might be a little weird to deal with that nothing, especially in context, because we now know like how we're going to use this. So we can get rid of the generic bits of that nothing and actually provide some meaning to what a nothing means in this, if that makes sense. So what we could do here is, and what is here for this? So this provides that. So we will provide that too. And this is going to be what we option it to because this is what the and we do option. So now that it's not a valid card, it still matches the old flow of this. And just to see that it matches the old flow, and remember, this isn't doing the fancy stuff. Well, I mean, I guess it is. What we'll do is replace this with imperative function. Oh, this doesn't return a maybe. All right. So to see that this would work, let's just do this. Okay, and we'll comment that out, and then here we'll do imperative function. Okay. And now we see it gets it back. It behaves just the same way that the other one did. So for instance, if we were to do 306X, we get back diners. And if we do some of this with a little bit of that, actually put things back the way they should be, then we still get back the diners. We can swap these out however we want, and we still get back the same results. So now we've matched that, but we did it in a way that we can do this, we can tag anything we want as long as we keep that formula, right? Okay, so now that we have this pair, what do we do with it? Well, there's a couple things we can do with it. So for instance, say we want to turn this into an object that has the card number and like something with number. So what we can do here is we'll do obj, and we'll use the one from Crocs. It's also available in Crocs. So we'll do obj number. And of course we need to bring that in. We don't need identity anymore. And now we see that we get back our number. We get an object that has the number added to it. Well, now we have this diners thing. So it would be really great if we were to put type or something along those lines, right? So what we can do here is use a clever little function called merge. So here, let's call this, well, I mean, we could do it that way. What would be a good name for this? Let's call this prep card for now. I don't know. We'll come up with a better name for it. What's it doing, though? So we'll call this tag card. Okay, so now this tags the actual card. It does the matching, does all that. That's an amazing name for it, Ian. Thank you very much. I appreciate that. And then what was the name of this function? That was card type from number. So let's call this card from number. Const card from number. And this is basically the only thing it's going to take, because we have the match card there, and that's all put in, is card from number, compose, and we want to do merge. Nope. Yeah. So we'll do tag card, and we'll do merge, which basically will merge the two pairs. And we'll do merge on ASOC, or ASOC. I call it ASOC. But this cool guy at work during his interview corrected me on that. So, oh, he is so cool too. I wish I could talk about him. He was awesome. Got to play around with the solution. Never mind. I don't want to talk work stuff. Okay, so we have ASOC. And what we want to do is associate the value to this to something else. So we'll call this type. So what this is going to do, let's bring these in, merge in assoc. We don't need this anymore. We're done with that. Merge goes here. And ASOC goes there. And here we'll just do card from number. And now we see we get back a number that has the type. So just by doing that real simple thing with this pair and just composing the tag card, we're able to actually take that pair and put it into something that we might be able to use later. But the beauty of this is we get to keep our state, and that's kind of the beauty of the pair. And then when we're ready to actually merge that state into something, because we could even fan out and branch and do other stuff there. No big deal. Yeah, I mean, I guess that's all the time I have right now. We only have a couple people watching, so yeah, I wanted to show another example, but I think I'll show that one next week. It's the same sort of thing around pairs, except we do kind of more about the parallelization of the pair than the tagging. Because you can think of pairs in many different ways, or product types in many different ways. So anyway, I think that's going to do it for me. Does anyone have any questions by any chance? I'm going to Jet, so you can use the chat. No? All right. Well, if you got any questions, comments, anything like that, feel free to leave them in the comments. I try to get back to them. Yeah, if you'd like to see more episodes or casts like this where we do solutions, then I need things to solve. So if you have any like imperative code that you want to see, like how you would approach thinking about it in terms of encoding to an ADT and like doing things like this where you just fold down, like build something out, fold it down, things like that. Hit me up on Twitter or put a comment somewhere. DM me on Twitter if you don't want to publicly like anything. This is actually wrong. Should be a maybe of B. Sorry about that. And then next week I'm going to do another little bit where we'll be playing with pair a little more. And I don't know, should be a blast. Well, I don't know if it's a blast, but it should be fun anyway. But thanks so much for joining me. Yeah, that's all I got. Have a great day.